All right, we're good to go. All right. So, let's start with any questions. The good news is once you turn in Lab 6, you're done with the traffic light for Engineering 250.
Yeah.
Yeah. The bad news is it comes back in Engineering 270, but it's a lot easier in that class.
Hopefully I can do it in person because Tinkerpad is terrible when I say that.
We're also done with Tinkercad after Lab 6. So
Ah,
that's potentially good news too.
What's Lab 7 with?
Lab 7 is just using
Verilog.
Aldec, so that HDL tool we've been using. And then 270, we don't use Tinkercad at all as far as I can remember. We use a different tool called MPLab, which you would end up using in person as well as online. But when it's in person, you also go in the lab and actually build circuits on a proto board. In the online version for this coming summer, we just use MPLab.
Is NP Lab like a big jump from Tinkercad in terms of performance, or is it just like much different to use?
MPLab is a totally different ball game. So Tinkercad is really, originally for designing 3D models and then also for putting things on circuit boards and so on. MPLab is a tool from the manufacturer who makes the chip we work with, and it's really designed to let you do simulation of this microprocessor, and it's used in industry. It's a pretty professional tool chain, and it works well for the most part. It doesn't have any of the sort of kind of strange behavior of the clock suddenly slowing down or things like that. So it's pretty solid. Any parting questions on Lab 6? So I'll get this graded when I can, but it might be a little while.
Not so much Lab 6, but I'm curious about class schedules next week because I noticed our assignments are due Monday and Tuesday next week versus Tuesday and Wednesday.
Mm-hmm.
So we're not going to have any more assignments after that. What's the buzz?
Yeah, I think that's it for the assignments.
Okay, so we're still having classes Tuesday and Thursday?
Oh yeah, definitely.
Cool.
Yeah, so we'll dig deeper into Verilog today. We'll play around with timing, and we'll start looking at what are called always blocks. So basically, designing circuits with flip flops using Verilog. And then Thursday, I think we'll jump into some state machine, playing around with some state machine circuits in Verilog using the Aldec tool. And then next week, not sure. So next Thursday will probably be like review and wrap up and questions about the exam and so on. And next Tuesday, we'll catch up with whatever is still to be done. We'll go back and pick up a few other things from the past and probably go through some of the stuff in Chapter 9 that we haven't done yet. So yeah, we'll have class every Tuesday, Thursday this week and next week.
I do have a question about the lab.
Yeah.
So the first part, and you've already answered this, the first experiment, it says to create a 2 to 4 second delay,
Mm-hmm.
and just assume that the 5x5 is set to 2 second delay.
Right.
Did you want like that controlled by a switch, or are you just wanting to create a 2 second delay on a 5x5?
So take the 5x5 from previous lab and hook that up. That 5x5 that we used before was doing a 2 to 4 second delay. So go ahead and use that, or was generating a 2 second pulse. So use that for experiment 1, that 5x5. So include the schematic in your schematics for experiment 1, and then copy that circuit in Tinkercad and use it for experiment 1, and then you'll use that for experiment 2.
Gotcha. I was just making it overly complicated. Awesome.
No, that's cool.
Thanks.
Yeah. And remember, you can get away with using one 555 for all 3 of your lane control circuits. You don't need 3 separate 555 circuits. They can all use the same 2-second pulse. And in fact, it works best if they use the same one because it keeps everything synchronized. Another thing to keep in mind, and I was glancing at some of the labs, remember if you have something like a 7404, it's got 6 inverters inside. Right, hooked up something like this. So if you need 6 inverters in your circuit, you can use a single 7404. If you need, 10 inverters, you can get away with 2 7404s. You definitely don't need 10 of these. And even if you have 3 lanes, if in the end you only needed, 9 or 10 inverters, you only need 2 of these packages. And maybe in Tinkercad it's easier to, totally replicate your circuit from one lane to the next and just have 3 copies of it. But if you're doing your schematic first, right, your schematic has no notion that you're using a 7404. It just sees, that you've got some AND gates and some inverters and some OR gates and so on. And you build your schematic, and then once you've got your logic, diagram with your logic symbols for gates and so on and so forth, then you say, how am I going to build this in Tinkercad? And you say, well, each of these is going to have to be a 7404. Okay, well, this can come from, package U1, 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 and you pick some pin numbers. And this is going to have to come from U2, and I'll pick some pin numbers there. And if I've got another OR gate somewhere, well, that can also come from that same chip, U2, and I'll use these pin numbers. And maybe this is going into another inverter. Well, let's see, U1, I've only used 4 of them. I can take my 5th one from here, and so that can go right there, right? And you do this before you ever open Tinkercad. You sketch this out on paper and have, your wiring diagram with whatever connections and so on. And once you have your logic diagram with the symbols, you put the part numbers and the pin numbers on it, and then when you've got this completely finished, then you open up Tinkercad and you grab a breadboard and you start grabbing parts. And as you're building this diagram, you're making your component ID block up here. So U1 is a 7404, U2 is a 7432, and so on. And so what do I need? Well, I need one of these and one of these and one of those and so on and so forth. And then, a good trick is make a copy of this, get yourself a highlighter, and as you start wiring, right, highlight your wires. So take a wire, and if this was, pin 4, put a wire between pin 2 of U1 and pin 4 of, maybe this is U3, and then, highlight this on your diagram, and just keep going until your whole diagram is highlighted. And so, yeah, the over, almost always what students do is they go straight to Tinkercad and they build on there first. And, that's fun to do, and I'll admit, sometimes when I'm designing a circuit, I'll start putting parts together before I actually, go down to this level. And for something quick and dirty, that will tend to work fine. For anything of fairly large scale, though, you're going to need the wiring diagram at some point, and you really want it to come first. And you can do it in parts, right? So we said you can do each lane independently, so you can make your full schematic for one lane, and then build that in Tinkercad and make sure it works. But then go back and, add in the other 2 lanes on your schematic, and go back and then add that circuitry. So you can still be building in Tinkercad while you're doing this, but it's probably cleanest if this always comes before putting the parts into the proto board, whether that's in Tinkercad or in the laboratory. Um, all right, let's see. What else can we say about this? So I glanced at a few labs already, and let me make the following offer. If go back and look at what you submitted in your lab and see if the schematic diagram is legible. Right? I want to be able to read part numbers and pin numbers cleanly. If it doesn't look legible to you, what I'm going to let you do is you know, rescan or blow up or reconvert or something those pictures to make them legible. And then go ahead and submit it late, but put a note on the submission saying, you know, this is the same lab with, you know, pictures that are easier to read. And if you get that in before I get to grading your lab, right, I won't count that as late. But I really want to be able to read your schematic diagram, because that's what I actually can use to see, you know, how you built the circuit, how you designed it, and so on and so forth. So if you're not sure, go back and double check your schematics. If you have a huge schematic, you can break it into pages, so you can have, you know, some sort of schematic here with gates and stuff like that. And, you know, label it at the end of your page with something, and then on the next page put that same label and continue. You know, or whatever. But you can also, depending on what you have to scan, you know, a PDF can shrink down so that it fits on one page, but can still be blown up, and have full resolution inside it. But you've got to scan it or convert it with the full resolution, and that can be tricky to do. So you can always break it into pages like that, and that'll work also. PDFs are nice though, because they can have like lots of detail. All right. Anything else? All right, let's play around with timing and glitches. So, when I tried doing this last week, the recording was not working very well with the software. So let me try just doing this on faith again and see if we can get lucky. Let me close some stuff out. All right, I'm gonna bring up the software. All right, so far so good. So let's make a new workspace. And I'm gonna call this timing test. And I'll create an empty design. We'll go with Verilog. So hopefully this is old hat to people at this point. And let's create a new Verilog source. All right, so what are we gonna do? I wanna play with timing diagrams. And we're going to revisit a circuit that we worked with a while ago, which was this kind of quirky, let's have an input, and let's put this into an AND gate. And let's take our input and also run it through an inverter and put that into the AND gate. And here's our output. And let me call the output of this inverter X. And let's make a truth table. So our input is either 0 or 1. X is the opposite of our input, so that's a 1 or a 0. And our output is in ANDed with X. Right, that's our two inputs, and 0 ANDed with 1 is 0, 1 ANDed with 0 is 0. So we would expect that, you know, as our input changes, our output is always going to be 0. Alright, so I want to build the circuit and see if this is what happens. So let's go ahead and make a timing test circuit, and we'll have an input called in, and we'll have an output called out. And we'll set out equal to the opposite of in, and so I'm going to make a wire called X.
Okay.
Question?
No, sorry, my bad.
Okay, no problem. Alright, so I'll make a wire called X. I'm going to set X equal to the inverse of in. And then I'm going to assign out equal to in ANDed with X.
Is wire like similar to like you say like a very?
It's basically declaring a variable, and it's saying it's just a plain old signal, so it can be given a value, but it doesn't remember what the value is. We're going to have a new way to declare variables later today, which is to say register or reg, and once we have that, it'll make more sense why sometimes we say wire. So I think this will compile, but I'm never quite sure until I try. So let's compile all. And that looks good. No errors, no warnings. Alright, so file new waveform. This will prepare us to simulate. And then simulation, initialize simulation. Select the top level. I'm going to go with timing test. This looks totally different from what we did last week, so I don't know what's up with that. But there's our top level. And I'm going to drag over in and X and out. And I'm going to set up my input with a stimulator. I'm just going to use a clock, which is popping up in a different window here. So input, we will set up a clock, and I'll go with 20 nanoseconds. And close. Alright, so let's go ahead and step this simulation a little. And you can see what's happening here, right? The input is toggling between high and low, high and low. And the output, the X, is the complement of the input. So when input goes low, high, X goes high, low, and the AND of those is always 0. So anywhere we look on here, the output's always 0. So that's the theoretical behavior of this circuit. And it matches, you know, what we got by making a truth table and just logically seeing that this is, you know, a logical AND. So that's great, but, you know, we know that the real world is different. We know that there's a propagation delay between the input and the output of our inverter. There's also a propagation delay between the inputs and the output of the AND gate, but this is the one that's going to be interesting to us. When the input changes, it's going to take a little while for the output to change. All right, so let's introduce a delay into our design. So I'll stop this simulation. I'll go back to my original design. And I'm going to do something different here. When I assign x to be the inverse of the input, I'm going to add a delay. So I'm going to say assign, I'm going to say number sign 5. X equals not in. And let me put a comment on here. And say this gate takes 5 nanoseconds to act. So that's what that number sign 5 means. And let me go ahead and add a delay down here. Let's set our AND gate to take 7 nanoseconds. Yeah, let me make it smaller. Oh, don't ever hit control left arrow with AVHDL when you're running in wine. It seems to be what I keep doing that kills this. So yeah, I just lost my software. Alright, so
I have a question about the timing delay there. So,
yeah.
Or not timing, but anything. So does it take decimal values? I mean, not that we'll have anything below a nanosecond, but
I think it'll take units. So if you wanted to do like fractions, you could do picoseconds.
okay.
I don't think he's recording again, by the way.
What do you mean?
I don't see the recording symbol.
Yeah, you said it wasn't working at the beginning, right?
You should never see a recording symbol as far as I know. Do you normally?
It's usually a little red dot at the top that says recording.
Really?
He doesn't use Zoom to record, so
Oh, okay.
Yeah.
record that.
Yeah, I just record locally.
Got it.
Alright, let's see how much progress we lost here. So, recent workspaces, timing test. We probably just lost the timing delays. Alright, not bad. So assign number sign 5. So the inverter takes 5 nanoseconds, and then assign number sign 2. And so the NAND gate takes 2 nanoseconds, and I will save it. We've still got our wire X. Okay, so let's go ahead and compile this. So design, compile all. That's good. Let's go ahead and say file, new waveform. And simulation initialize. Pick your top level module. Nope, it already remembered. And we'll look at our input, our output, and our final circuit value. We'll set up a stimulator. And we'll do our clock. And yeah, we'll leave our clock at 100 nanoseconds. We'll give it some time. Alright, so we'll apply and close. Alright, you ready for this? So now we're going to go ahead and step the simulation. And you see something different happening. Right, our circuit output out, let me move it back down to the bottom. It's got a little glitch. Right, this should be low all the time, but it pulses high every now and then. In particular, when our input signal changes from a 0 to a 1, at this point the input is 1 and this X signal, the output of the inverter, is still a 1 because the inverter doesn't respond until you get over here. And so for this period of time, from here to here, both inputs to the AND gate are 1. And so a few ticks after that, the AND gate outputs a 1. So this is capturing the fact that when this is a 1, this is a 1, this is a 0, the output's clearly going to be a 0. When we change this to a 0, this goes to a 0. We have a 0, 0 for a while, and then eventually this goes to a 1. So the output is still a 0. But then when we raise this to a 1 again, this goes immediately to a 1 because it's just traveling along a wire. But it'll take a little bit of time before the output of the inverter changes to a 0. So right now we've got a pair of 1s going in, and so the output of the AND gate's going to be a 1. And then eventually the inverter will say, oh yeah, I should output a 0, and it'll change to a 0. So it's on that rise of the input from a 0 to 1 that we get this little glitch. Now how big is this glitch? Well, 152 nanoseconds over to 157, that's a 5 nanosecond glitch. That's forever, right? If you have a 3 gigahertz clock, that's 15 clock ticks that happened while this input was a 1. And that's significant. So that's why we talk about clocked circuits. That's why we talk about state machines that we've been talking about for the past few weeks, is because we don't want to just take inputs and have them drive outputs and just do whatever those outputs tell us. We would have a clock ticking, and the clock would tick, you know, after these glitches have gone away. So we'd tick the clock right here, and we'd say, oh, we've got a 0, and we'd tick the clock here, and we say, oh, we got a 0, and we never see those little noises. All right, so we can play with timing by using this kind of notation, so we can introduce delays. All right, so questions on that? And this is in that quick intro to Verilog. There's a section that talks about this.
So any kind of delay you want to assign to any given input or output, you can do it with just the hashtag in front of the assignment. Okay.
Yeah, that's correct. And if we did something maybe a little more realistic, so an AND gate is a little more complex than a NOT, so maybe this would take 12 nanoseconds. So let's save that. And let's recompile. And then go back here. Let's stop the simulation. Yeah, so here we've made the AND gate much slower, and it's slow enough that it doesn't actually notice that glitch in the inputs. Right, for 5 nanoseconds, both inputs are a 1, but since the AND gate, we change the delay to say it's going to take 12 nanoseconds, right? By the time it generates an output, both of its inputs are 0. That may or may not be what happens realistically if we use actual physical devices for this. Because 12 nanoseconds, well, what's happening during that 12 nanoseconds? Who knows, right? It depends on the physics of the device. But if we make the AND gate fast enough that it has a chance to see those delays, then we'll reproduce that glitchy behavior.
What did you set the stimulator for into?
I just set it up as a clock. So I think it was a 100 nanosecond clock.
And out is also a clock?
So the only stimulator I set up was in, because that's the only real input to our circuit. Right? X is driven by the output of an inverter, and out is driven by the output of an AND gate. So that's the only thing I had to specify the input value for. But the effect is, you know, X is a clock with the same frequency as the input, but with what we would call a phase shift. And then out is, you know, whatever the output of that AND gate is. So it's also a clock with a 10 megahertz frequency, but a different duty cycle, right? It's mostly low and it goes high every 100 nanoseconds. And a lot of times if you have a clock feeding into a circuit, the outputs are also going to be periodic, so clock-like, but not because we drove them with a clock, but because, you know, that's what the circuitry is doing. And, you know, you can change the input to be random. Random is kind of fun.
I'm not seeing the glitches of 0 to 1.
You're not seeing them here, or are you trying it on your system?
I'm trying out my system.
Okay. And you definitely have the number sign 5, number sign 1 on those assignment statements?
Yep.
When you look at the timing diagram, do you see a delay if you zoom in between, say, the input and that intermediate point X?
Yeah, I see a little delay there.
But no glitches. So the glitches.
I saw it a second ago.
So it might be a matter of scale. The glitches are only going to be like 5 nanoseconds wide, so you might have to zoom in. Because like if I zoom out too far, well, I still kind of see them. Yeah, play around with the scale that you're looking at and see if that helps.
It seems like there's a little gap between every in and out so that there couldn't be a glitch. I'll share it with you later.
Okay. Yeah, come by Officer Lab. We can look at it. All right. Other questions, comments?
This is probably way back, and I probably should have asked this earlier. What was the source that you set this in? Because I was trying to like follow you, and then I kind of lost a little bit in the middle. So it was just you would go like, well, like for some reason, would you just put the wire, or not the wire? You put the input and X as inputs, correct?
Yeah, like this. You mean the source code?
Correct.
Yeah. So I said wire X, just make that kind of a temporary variable.
Okay.
I assigned X to exclamation mark in, which means the inverse of in. I think you can use a tilde also.
Alright. Oh, okay. I see where I got wrong. I just didn't. Okay. Sweet.
And then out is just the AND gate.
Mm-hmm. Good. Thank you.
All right, you're welcome. All right, so we were playing around last time with this idea of behavioral Verilog, where, for example, if we wanted to add two numbers together, we could just do something as simple as assign x equals a plus b. And the Verilog compiler knew that this meant we needed an adder, and if we did something like, you know, wire 1:0 A and the same for B, it knew that we needed a 2-bit adder, and this would create, you know, some kind of block that we could feed two 2-bit numbers into and produce a 3-bit sum, and it would build, you know, the logic with the XORs and the half adder, full adder, and all of that stuff, right? Just by saying x equals a plus b, right? So this was not saying, you know, I've made a truth table and a k-map and an equation, and here's you know, where you should put AND gates and OR gates together. This is saying I want to add these numbers together, put the result in x. And we're letting the compiler do what it needs to do to build a circuit that does that. This is what we do when we write programs in a high-level language like C, right? If we want to find the square root of a number, we say, you know, y equals square root of x. Well, most hardware doesn't know how to compute a square root. You have to go through a series of steps to compute a square root. You use something like Newton's method, right? But we don't have to specify the instructions for that because our compiler knows that when we say, you know, SQRT of x, it should do all the stuff that, you know, somebody told it ahead of time how to do. Same thing with this. So let's take a look at a multiplexer. And let's think about just a 2 to 1. So here's input 0, here's input 1. Here's our select. Here's our output. And the behavior we want is the following. If our select input is a 0, we want our output to be whatever's coming in on I0. If our select input is 1, we want the output to be whatever's coming in on I1. So this is this 2 to 1 selection circuit that at runtime, if you like, connects either this input to the output or connects that input to the output. And we can change which of those is connected to the output by just changing the value of this 1-bit input. And so this is not a usual truth table because we don't have just ones or zeros here. We've got, you know, these signal names here. But we can turn this into a truth table by having, you know, a column for I0, a column for I1 on the inputs, and then filling in the ones or the zeros. And we can make a K-map, and we can make equations and all that kind of stuff, right? But this is really the behavior that we're after, right? So our behavior is if our select equals 1, if our select equals 0, out should be I0. Otherwise, out should be I1. And so we can use this notion of what our circuit should do to actually write our Verilog code. And we're not going to use an if statement, but we're going to use this ternary operator. So let's close this workspace. Which is never as easy as I think it should be. Let's see. Do you wish to save it? No. Okay. And let's close workspace. Okay. All right. So let's start totally new project. So we'll say new workspace, and let's call this mux test. So we'll create an empty design, use Verilog, we'll call it mux test, we'll finish, we'll go ahead and we'll create a new Verilog source. This is like tiny little print for me. Verilog source. Mux test. Alright, so we need 3 inputs, I0, I1 select, and 1 output out. And all of these things are 1 bit. So we'll make a new input, I0. We'll make an input, I1. We'll make an input, select. And we'll make an output called out, which I'll mark as an output. All right, so there's our base of our Verilog code. And there's our one-line description of what our circuit should do. So I'm using this ternary operator which says see if select is equal to 1. And if it is, set my output equal to I1. Otherwise set it equal to I0. And I better be careful with upper lowercase here. All right, so if select's equal to 1, output will be equal to the thing on the left of the colon, which is I1. Otherwise, output will be equal to the thing on the right of the colon, which is I0. So this is like the ternary operator in C. And that should be enough to define our multiplexer. So let me save that. Let me go to Design, Compile All. Compiler is happy. We'll go ahead and file new waveform. And simulation initialize. Select the top level, mux test. Pick the one with the star next to it, apply and OK. And now I'm just going to grab all of these and pull them in. And this time I want to stimulate I0, I1, and select. And we'll look at what the output is in response. So I'm going to set up 3 stimulators. So I0 I'm going to set up to a clock, and I'll make that a 20 nanosecond clock. I1 I'm going to make a 40 nanosecond clock. And select I'm going to make an 80 nanosecond. Select I'll make slower. Let's make this a 200 nanosecond clock. So what I'm doing is I'm trying to pick different values for my input so that I eventually get all possible combinations. But the main behavior we should see here is that the select line should be sending either I0 or I1 to the output. So I'm going to leave my select line low for 100 nanoseconds, and then I'm going to set it high for 100 nanoseconds and see what it does. So I'll close this and we'll just step through the simulation a few ticks. And then let's zoom out and let's see what's happening. So here's the select line. This is the one that's choosing which input goes to the output. Over here you can see the input is low, the select line is low, and the output is matching this input up here, the fast one. When the select line goes high, like right here, now the output is matching this slow input, input 1. And any time that the select line is low, the output matches I0. When the select line's high, the output matches I1. So we're using 2 different inputs that are easy to see. One of them is fast, one of them is slow, and you can see which one's being routed to the output. So that's a 2-to-1 selector. And we didn't have to do any kind of, equations, K-maps, sum of products, anything like that. It was 1 line of Verilog, which just set the output equal to either I1 or I0. All right, so our next step in all of this is to look at events and circuits that are doing something based on some event. And when we talk about events, we're almost always talking about a clock. So we want to look at building circuits that have clocks in them, basically state machines. But we're not going to do, the state transition table and the excitation table and flip-flops and all of that stuff. We're going to skip all of that. We're going to look at the behavior that we're after. What do we want this circuit to do? Okay, how do we want it to act? And this is going to get into some particular syntax that I'll highlight as we work with it. But it's going to be important. So let's start with a simple example. Suppose we want to make, for some reason, a clocked AND gate. Okay, so we want something like this. A circuit with two inputs, A and B, and a clock, and an output. And we want our output to be A and B, but we only want this when the clock ticks. So this is something we would build with a flip-flop and an AND gate and some other logic. But the effect is we want this to have an output value that is fixed. It never changes except when the clock ticks. And when the clock ticks, we want to take what the current values of A and B are, we want to AND them logically and set the output equal to that value. And that's it. Then the output is rock solid, stable, totally fixed. We can change the inputs, has no effect until the next clock tick. Next clock tick, if this is a 0 and a 1, the output goes to a 0. Next clock tick, if this is a 1 and a 1, the output goes to a 1. Alright, everybody got the idea of what we're after here? Forget about why we want this because it's a silly circuit. But that's the goal, is the output only changes when the clock ticks. So let's write some Verilog.
You'd never do that, though, right?
Say again?
You'd never do something like that, though.
Well,
the clock AND gate.
We'd probably take an AND gate and feed it to the D input of a flip-flop, and then use the clock to toggle the flip-flop. So the effect of this would be, you know, we'd take A and B and maybe AND them and put that into a D flip-flop. We'd have our clock, and this would be our output. So this is the circuit that we're designing. But I'm thinking of it, you know, even more simply than this, as just sort of this clocked logic gate. But yeah, we might do something like this. I mean, in general, we have lots of combinational logic that feeds our flip-flops. So it could be part of a state machine or something. But I'm not planning to do anything with this. It's purely just an exercise in Verilog. Alright, so let's close workspace. I don't seem to be able to close everything with just one click. I'm answering questions on the side here. Oh, that worked. Okay, good. Alright, so let's make a new workspace. And I'm going to call this clock AND. So we'll create an empty design, we'll go with Verilog, and I'm going to call it clock AND, and I'm going to create a new Verilog source. It's called clock AND. Alright, so what do we need here? We need inputs A, B, clock, we need output out. Alright, so I'll have an input A, input B, input clock, and out, which will be an output. There's our good system diagram. We're all set. Alright, so if I say something like assign out equals A and B, that's creating a wire. It's connecting A and B to the inputs of an AND gate. It's connecting the output of the AND gate to this port out. And that's going to be a simple AND gate. Whatever A and B are, that's going to be what appears on the output. That's not what I'm after. What I really want to do is remember some value for my output, but when that clock ticks, I want to change that value and set it equal to A and B. So the logic is something like this. So when clock ticks, set the output equal to A and B. That's what I'm after in words. Now, I can't make this an assignment statement, because assign, remember, is just sort of connecting a wire, and I can't say, you know, when the clock ticks, go ahead and connect the output of this AND gate to this port, because we can't make and unmake wired connections based on a clock tick, right? So we're not going to use the assignment statement here. And we're going to need some kind of flip-flop. Anytime that you're talking about remembering a value, you need some sort of memory. And that means a flip-flop. And flip-flops in Verilog are usually called registers. So we're going to have a new piece of language in here. We're going to introduce something called a register. And I declare a register with just reg. So I'm going to make a register called temp. And reg usually means make a flip-flop. Alright, so that's one new keyword is reg, reg. And reg declares something to be a variable that can remember a value. So we can say, you know, temp is equal to something, and it will remember that value. Okay, the other keyword we're going to introduce is always. And always is how we say when some event occurs, I want something to happen. And our always block is going to look like this. So we're going to say always @ sign, and I'm going to say positive edge of clock. So do the following when the clock ticks from 0 to 1. Oh, I hit the control backspace again. Oh, okay, I crashed. Oh man, I lost like 2 lines of code.
That's gotta be a hard habit to break.
It is.
Control backspace all the time.
Here's
Control backspace.
it's actually Ctrl-arrow key that I'm using to go back. I wanted to go back and change tricks to ticks. And so if you do Control left arrow, it goes back an entire word. And so 2 of those will get me back to the T. And it's just a keyboard habit. And for some reason, when I'm running this software tool under Wine in Linux, that always brings up this window that says, you know, some exception has occurred. Fortunately, this has happened enough times that I'll show you what we do. So we do a pgrep, we find out the process ID of this, we kill it with a hard kill, and then we rerun wine. And that brings it back. The good thing about recurring bugs in software is you get really good habits for fixing them. Alright, so back into our clocked AND. Alright, so always at positive edge clock begin. So do these statements when the clock ticks from 0 to 1. Got rid of my indenting for me. Okay, that's fine. Alright, so what I want to do when the clock ticks is I want to say, now let's set x equal to the AND of A with B. Alright, so I'm going to say and we use a special symbol for storing into a register. It's a less than sign followed by an equal, so it looks like a big arrow. x is set equal to a and b. And it's really important that you don't just use a plain equals sign. Got to use a less than followed by an equal.
What for?
Magic. So we'll dig into this later, but this is what's called a non-blocking assignment statement. And if we use a single equal sign, it will compile fine, and it will run fine sometimes. And then when you turn it in and your teacher tests it, it won't work. And it's really annoying because you don't get a compile error, and it actually works in some cases. But a single equal sign is what's called a blocking assignment statement. And a blocking assignment statement says, first do this assignment, then do the next assignment, then do the next assignment. It does them sequentially the way we would in a programming language. And that's not how hardware works. Hardware is massively parallel. If I have 5 assignments, they should all happen at the same time. If I have 5 flip-flops and each of them changes their output in response to a clock tick, and those outputs go into other logic, that should all happen simultaneously, right? That's hardware, it's parallel. But if I write my Verilog code with an equal sign instead of a less than equal, it's not parallel anymore. Stuff happens sequentially. And it really short circuits the whole advantage of using hardware versus software, which is parallelism. But it's valid syntax, and there might be cases where you actually want that sequential behavior so the compiler won't say anything about it. And when you run your code, if you don't look at it too closely, it'll look like your code's working fine. So we want to get in the habit, anytime that we're inside an always block, always use this less than equals to do assignment.
Can you use a greater than equals?
No, I don't think that's valid syntax. But that would look like you were assigning something to the right if you did that, and I don't think it understands that. So
That's really weird.
Just think of it as one quirky double width symbol, like an arrow, you know. And in some fonts it looks better, in some it looks worse. This one looks pretty weird.
You got ligatures.
Yeah. So, yeah, so that's just what we're going to use inside an always block. So our always block is really simple here, right? It's one statement, which is, you know, when the clock ticks from 0 to 1, the positive edge of the clock, we're going to set x equal to the end of a and b. And then I'm going to put an end statement here. And the end statement at the end of a begin statement does not get a semicolon, and the begin does not get a semicolon. Annoying, I know. But that's what it does. I'm going to save that before it crashes. I'm going to get rid of this comment. Alright, so begin and end, these are like curly brackets if you used other languages. This basically lets us put in one or more statements, and then the end basically ends the always block. So everything between begin and end will happen when the clock ticks. So what this line of Verilog says is whenever the clock ticks from 0 to 1, let's set x equal to the and of a with b. So this should be a clocked AND gate. And except I don't want to do. Yeah, I don't want x, I want temp. Alright, so we're going to set.
Confused about that as well.
Yeah, thank you. So temp gets set equal to that. What we want is we want the output to be this clocked value. So now I'm going to use an assign statement and set out equal to temp.
What? That's never mind.
There's a number of potential questions at this point. But the if
Because what if, I mean, I don't really understand how often this code runs, but what if it's not on, what if the always doesn't run and then just assigns out to temp or something, I don't know.
so if when the always runs, temp will change a value, right? It'll be set equal to the and of of A and B. But out is always equal to whatever temp is. So and temp is a register, right? It's basically a flip-flop. So out is basically connected directly to the Q output of a flip-flop. But this block says, what should we do when the clock ticks? Well, we should take A and B and them together, and then do whatever you have to do to make this temp, this output of this flip-flop, equal to that AND. And the compiler will have to figure out how to make this happen, right? But we're describing what behavior we want. We want to calculate this AND on the clock tick, and we always want our output to be whatever that value was that was calculated. But this is only going to happen, this statement only happens when the clock ticks. So, don't double click either, because that also crashes the tool. So this assignment statement happens at a point in time, right? It's just when the clock ticks. This is our usual game when we play with flip-flops, right? The whole things that are changing the inputs of the flip-flops, no effect on the outputs, except at the moment when the clock ticks, right? That's what these always blocks are doing. They're basically saying what should happen in that moment, at that knife edge of the clock, changing, in this case, in the positive direction from a 0 to a 1. And it's just going to change this flip-flop value, temp, to be whatever this AND is. This assignment statement is a wiring connection. It's not dependent on a clock event or any other event. It permanently sets out equal to whatever the value of this flip-flop is. And it's...
Okay, so,
Go ahead.
so for the very first thing before the clock ticks once, what is the value of out going to be? Is it going to be 0 or 1? Is it going to be like in circuits where it's just kind of random? Or?
Well, that's a good question. So in physical hardware, it would be a basically random value. In the simulator, it'll probably show up as a red line in the middle between 0 and 1, saying, I don't have a value for this yet. Because the simulator usually won't make assumptions. So it'll probably show up as undefined, but the first time the clock ticks, temp should get a value, and then out should go high or low.
Okay, cool. Yeah, that's what I mean.
All right. And yeah, I got an error here, so here's what it's complaining about. And if I was not so tired, I would go through and try to figure out what this means, and then I would have no idea. But so let's go ahead and run that again. And we'll do recent workspaces, clock and I saved it, fortunately. So yeah, so that's our circuit. And what will this actually turn into in hardware? Sometimes you can make a educated guess, but it's going to be something pretty close to this, right? Clock is certainly going to feed the input of a flip-flop. It's probably going to be a D flip-flop, and the D input will probably be fed from A and B. This will be temp, and it'll also be out. So let's, yeah.
So when you do the assign out equals temp there, basically what you're doing is whatever the output of the register temp is at the time of the clock, that's what the out is going to be, right?
Yes, yes.
Okay, just making sure.
All right, so let's simulate this. So we'll do a new waveform. We'll simulation initialize. We'll pick a top level module. The design working libraries. Oh, I forgot to compile. Yes, let's compile. Okay, no errors. Initialize simulation. All right, so we got A, B, and clocks. So let's set up some stimulators. So for A, we'll just go with a 20 nanosecond. And for B, we'll go with 40 nanoseconds. And for our clock, oh, I don't know. Let's go with 55 nanoseconds. No, let's go with 23 nanoseconds. Okay, I got a reason. All right, let's go ahead and run this. All right, so back here in the beginning, you can see that temp and out show a value of X, and it's got a line at the top and a line at the bottom, and it's yellow in the middle. So that's the undefined region. So as you were asking, right, before the first clock tick, we don't know what these values are because we haven't done that always block yet. So somewhere right here. So now here A goes up to a 1, but still haven't had a clock tick. And then right here the clock ticks. And so at this point the output is set equal to A ANDed with B. Well, A is a 1, B is a 0, so temp and out are equal to 0. Let me zoom out some, that's pretty good. Alright, so over here we've got a 0, 1. Output is still 0. Over here we've got a 1 and a 1, so A and B are both 1, but the output is still 0. Why? Because the clock hasn't ticked yet. But then right here, the clock ticks, and that's where the output goes to a 1. It changes to the AND of the two inputs.
Did you, quick question.
Yeah.
You put some sort of like pound sign delay on one of the inputs or outputs on the Verilog script?
No, I didn't.
Interesting, because like at that edge you're looking at right there,
Mm-hmm.
the one that says 34,652
Yeah.
picoseconds, it's saying 34,500 for me.
Oh, it depends where you are. So if I go right on that edge, there's 503. That's just where my cursor happens to be.
Oh.
So there's 34,500. So I was just off a little bit.
Mine like snaps to the edges.
Oh, nice. Okay, yeah, there should be a way to turn on snapping. All right, so here the output is 1, and here, for example, both inputs are 0, but the output is still 1. So the output's only changing on the clock tick. And then when the clock ticks 0 to 1, the output changes accordingly. The clock tick from 1 to 0 is not a clock event, right? We said at the positive edge of the clock, and so this only happens when the clock changes from 0 to 1, not on these falling edges. Now if we come in here and we change this to negative edge, I'm like all nervous now about like moving around too much. I killed it. Oh, but I learned another trick. So when it dies, if instead of saying close, you say show details and then close the detail window, then you don't have to kill the process by hand. So every time I teach this class, I learn a new batch of tricks for dealing with new quirks. Alright. The good side... Sorry?
You really ought to just dual boot for this.
Yeah.
For this thing that seems to crash a ton.
The good news is it's free software. What's really a pain is when you pay like $100,000 for your software, and this is what happens. Alright, so we're at the negative edge of the clock. I'm not going to change my comment because that seems to get me into trouble. But let's just go ahead and recompile and simulate this. Oh, we shouldn't have done that. I forgot my new waveform. I don't know if we really need to do this because we already did this, and I'm just showing the negative clock edge. Alright, so I don't know what frequencies we had, but we'll just pick something nominal. So we'll go with 20 nanoseconds for A and 40 nanoseconds for B. And then something weird like 23 nanoseconds for C. So the punchline here is when the clock changes from 0 to 1, like right here, the output is still stable. When the clock changes from 1 to 0, that's when the output responds and becomes the AND of the inputs. And so that's just the effect of saying negative edge clock. All right, let's do a 5-minute break, and then we'll look at more things we can do with this. We'll look at some more reasonable things like making counters and memories and things like that using this this notion of an always block. So let's do a 5-minute break.
Just a quick question.
Yeah.
Before we leave. This is recorded, correct?
As far as I know, I believe I'm still recording it.
Okay, sweet. Because I have to leave now because something just came up. So.
Okay.
All right, sweet. Thank you.
All right. All right, we'll be back in a few minutes. Alrighty. So let's keep going. So let's make a counter. So how does a counter work? It's a block. There's a clock input. And there's some sort of output. If we want a 4-bit counter, for example, it's a 4-bit output. And the idea is every time that the clock ticks, the output should go up by 1. And here we are going to have to deal with this business of what about unknown values. Because my Verilog code is basically going to be an always block, and I'm going to say when the clock ticks, let's set the output equal to the current output plus 1. So let's start that, but then we'll see a small complication. So let me close all of this. So we'll do a new workspace. We'll call it counter test. Verilog. And we'll do a new Verilog source. Counter test. So our input's going to be a clock. And then our output I'm just going to call out, but I'm going to make this a 4-bit counter. So we're going to do an array for our output, and that's going to go from 3 to 0. So that's an output. Alright, so there's our starting block. Alright, so we're going to use an always block. So always at pause edge clock begin. So I'd like to do this. Out is assigned out plus 1. But I'm going to do a few things in here. So my out is set up as a wire right now. And well, let's go for broke. Let's just make this thing a register. So out is still the output of our circuit, so it's a 3-bit output. I'm going to declare it to be a register. And I'm going to say at the positive edge of the clock, let's set output equal to output plus 1. And let's try to compile that. Alright, so that compiles fine. If I try to simulate this though, I'm going to get undefined values because of the same thing that we saw before. If I don't know what the current value of output is, how do I know what out plus 1 is equal to? So I'm going to add one other thing to my circuit. I'm going to add a reset input. And this reset is what I'm going to use to force the output to go to a known value. So I'm going to have one more input up here. So I'm going to have clock, reset, and out. And clock is a wire. And reset will be a wire. And then out will be our register. And now I'm going to change my always statement as follows. So on the clock tick, I'm going to do the following. If reset is equal to 1, begin. Out's going to get assigned the value of 0. And I'm probably going to mess up this syntax. All right, let's see if this compiles. If not, then I'll dig into the syntax. That worked way
Could
too.
you use the ternary statement for that?
Say again?
Couldn't you just do a ternary statement for that?
Yes, I could. I could do out as assigned, reset equals 1, question mark, 0, colon, out plus 1. Yeah, let's do that after this, because I believe that'll work also. Let's see if this works. So if reset equals 1, I'm going to set out to 0, otherwise I'm going to set out to out plus 1. So let's simulate this. So we'll do a new waveform. Initialize a simulation. Top level is count test. We'll have clock reset and out. Alright, so let me add some stimulators. So for reset, I'm going to use a formula. So I'm going to initialize it to 0. Actually, I'll initialize it to 1 at 0 nanoseconds, and then I'll bring it down to 0 after 50 nanoseconds. So I'm just going to raise the reset line originally, keep it high for 50 nanoseconds, and then drop it low. And then my clock, stimulators, I'll make that a clock, and I'll do 20 nanoseconds. All right, and let's run this thing. And so if you come back here to the beginning, for the first few nanoseconds, the output value shows up as X. Doesn't know what the value is. The reset line is high, but it doesn't take effect until the clock ticks. So here's the first clock tick. At that point, the reset line is high. That drives the clock down, the output value to a 0. And you can see there's a 0 right there. And then on the next rising edge of the clock, so here the clock ticked again, but the reset line was still held high, so the output is still a 0. And then at this point the reset line drops, and on this clock edge the output goes to 1, and then 2, 3, 4, 5, 6, 7, and it should count all the way up to F. D, E, F, and then it goes back to a 0. So like that. And you can expand the output and see it as the 4 individual traces, and you get this pattern that you start to recognize after a while, which is the least significant bit changes most rapidly, and it changes at half the clock frequency. The next least significant bit changes at half of that least significant bit's frequency. The next bit is half of that frequency, and so on. And in this case, bit 3, the most significant bit, changes most slowly. And it's half the frequency of bit 2. And you can look at this at any point and see the individual bit values. 1001, that's the binary number 9. So that's a counter, and you know, to build this is a state machine, right? We have we have 16 different states the machine can be in, and basically each time the clock ticks, we move from, you know, state 12 to state 13. And it's a Mora machine where if we're in state 13, the output of our machine is the value 13. And so to build this, you know, we'd need 4 flip-flops and a little bit of glue logic depending on the type of flip-flops. To set it up in Verilog, it's just an if-then-else. And let's see if we could do this with a ternary operator. So like that. So set the output to either a 0 or output +1.
What did you set the stimulators for clock and reset again? Or
we'll go back and take a look at them in a second.
Okay.
Let's see. Let's compile this while we're here.
Do you
Okay.
have to put the if statement for the ternary thing? You have to put it in parentheses.
I don't know. It depends on what it considers priorities of syntax. But if you're not sure, always put in parentheses. They never hurt, and they almost always help. In some languages, for example in C, there's lots of cases where you can leave off parentheses and you won't get a compile error, but it'll do something different from what you think. I don't know where Verilog falls on the spectrum of, you know, very, very picky about syntax. If there's any chance of ambiguity, I'll call an error, versus C or assembly language where it's like, yeah, I'll do what you said. Doesn't make any sense, but I'll do it anyway. So I'm going to use those just to be clear, but I honestly don't know if you take them off. I mean, we can see if we'll get a syntax error. But even if we don't, it's not guaranteed it's going to do the right thing. I feel like that's going to give us a syntax error, though. Nope, that compiled. But like I say, I don't know if it's going to do the right thing. So I'm going to leave those in. Alright, so if we run this, it should do exactly the same thing. So my stimulator for the reset was a formula where I said well, I typed it in up here, but here it is. Basically start at at a value of 1 at 0 nanoseconds, and then go to a value of 0 at 50 nanoseconds. So that's just a fixed formula which specifies the values over time. And then for the clock, I just did a plain old 20 nanosecond clock, so 50 megahertz.
Thank you.
Yep, you're welcome. Alright, suppose we want to make a subtractor, something that counts down. There you go. Just set your output -1. Let's go ahead, design, compile all, go back to our simulation, and rerun the simulation. And you can see it counts from 0 to F, E, D, C, B, A, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, and then back to F. So now we got a countdown circuit. So suppose we wanted a circuit that had another input, which lets you specify whether it's going to count up or down. So I'm going to have an input called up. And if that input's equal to 1, it's going to count up. If it's equal to 0, it's going to count down. So now we've got a more complex state machine. It has this additional input that controls what the new state is based on the previous state. And the diagram would be, you know, something like state 2, state 3, state 4. And if this is up equals 1, state 3 should go to state 4. If up is equal to 0, state 3 should go to state 2, and so on. And the Verilog for this is pretty straightforward. So we'll add another input. So we'll have this input. So if up is equal to 1, then we're going to set out equal to out plus 1. So if up is 1, we'll set out equal to out plus 1 or 0. Otherwise, we'll set out equal to out minus 1 or 0. So let's compile that. Let's go back to our simulation. And let's see. Let's initialize simulation. So we also have an up. I did compile it. So let's have an up input, and let's set this to be stimulated with a hotkey. So I'm going to just go over here and I'm going to hit the letter U, and I'm going to use that to toggle my up down. And so let's go ahead and start the simulation. So it looks like up is a 0 right now. So I'll tick the clock a few times, and now I'm going to hit the letter, I'm going to click inside here and just hit the letter U, and you'll see a message here which said up /1, and now I'm going to tick the simulation a few more times. And then I'm going to hit the letter U again and tick the simulation a few more times. And then hit the letter U again and go a few more times. And let's see what we've got here. So a little hard to see, but up is equal to a 0 all along here, and you can see it's counting down 9, 8, 7, 6, 5, 4, 3. And then I changed up to be a 1, and so the next clock tick it went from a 3 to a 4, 5, 6, 7, 8, 9. I'm playing weird zoom games here. Here up is a 0, and so it's counting down. It counts down to 0, F, E. And then when I raise up to a 1, it counts up to F, 0, 1, 2, 3, 4, and goes up. So there's an up-down counter. And it has a reset input. It has an up-down. It has a 4-bit output. Right? And it's this kind of machine. System diagram view. And Verilog code, you know, half dozen lines of Verilog. So this is why we use these hardware definition languages, because they let us capture and describe complex behavior with, you know, really just a few lines of code.
It's kind of magic.
It really is. And particularly after, you know, doing truth tables and K-maps and all of this kind of stuff, having this kind of capability is just fantastic. All right, so let's play with one. Yeah.
Is there not equals?
Yeah. So you can do exclamation mark equals.
Equals 1. Can you do bang for bang?
So you can do like this for not equals.
Cool.
Yeah. All right. So let's make a shift register. And this will pop up in your homework and your lab 7. So this is a good one to think about. A shift register, we looked at these briefly and we said, you know, we could take a series of flip-flops. And if we take the output of one and feed that to the input of another, and we tie all their clocks together, the effect is that whatever value you have here, the first time you clock the tick will move down, the first time you tick the clock will move down to this output, but it won't run all the way through from here to there. It will move down one stage per clock tick. And so whatever values you have here, when you tick the clock, the effect is this becomes A, this becomes B, this becomes C, this becomes D, and E disappears. And each time you tick, these values move down one spot. And so let's just make a really short shift register. Let's just make a shift register with 3 stages to it. And let's see what this looks like in Verilog. And this is where we're going to talk again about blocking versus non-blocking assignment statements. So let's do a new workspace. We'll call it SR1 for shift register 1. Verilog. SR1. Alright, so we're definitely going to have a clock input. And we're going to have, you know, some in, and we're going to have some output. Alright, so I'm going to have an input here. I'm going to call this Q1, Q2. And this is going to be our output, Q3, or something like that. The names aren't too critical, because it's going to be really obvious what's happening here. So I'm going to make a register Q1, register Q2. I'll go ahead and make a register Q3. So these are outputs of 3 flip-flops. I'm not going to correct my typo, because that's how I get into trouble. Alright, so always at the positive edge of the clock, let's do the following. So I'm going to set I'm going to set Q1 to be equal to whatever our input value is. I'm going to set Q2 to be whatever Q1 is. I'm going to set Q3 to be whatever Q2 is. And that's going to be the end of my always block. And I'm just going to assign my output to be equal to Q3, because that's the output of the whole circuit. Alright, so what's the setup here? The clock ticks, the input goes into Q1, Q1 goes into Q2, Q2 goes into Q3. So let's draw a picture of this. Alright, clock ticks, input should go here, this should go there, this should go there, which is the output. So this should be a 3-stage shift register. Alright, let's compile it. Compiles fine. Do a new waveform. Initialize, top module.
Could you go back to the Verilog page one more time, really
Sure.
quick? Weird.
You thinking about the order of these?
Oh, that is in the wrong spot. Not gonna batch compile. I was just curious.
Oh, okay. Cool. All right, so I'm going to set my input to randomize. So we'll just go with random, and we'll just randomize it every 20 nanoseconds. And our clock, we'll just do a 10 nanosecond. We'll do a 20 nanosecond clock. So our clock's going to keep ticking. Our input is going to be random. We might have to change it to be something more interesting. And we'll have Q1, Q2, Q3, and our output is just going to be whatever the output is. So let's go ahead and run this.
What's the clock speed at?
I did 20 nanoseconds.
Okay.
Which is also what I did my my random interval on my input. All right, so here's our waveform. And let me get rid of my output signal. Let's just look at the 3 flip-flop values. Right? So this is classic shift register behavior. Right? And I'm zoomed in a weird way, so this will scroll around. But you know, here our input went to a 1. Next clock tick that ended up in Q2, next clock tick, or Q1, next tick Q2, next tick Q3. And here's where the input dropped to a 0, and you can see that works its way through the shift register on each clock tick. And so each stage is a slightly delayed version of the previous stage. And Q1 is a slightly delayed version of the input. And when you see this kind of thing, you're looking at a shift register. And you've seen this before, right? Anybody want to venture where you've encountered this?
Kind of in the counter lab we had.
Yeah, you saw this in the counter lab. You also saw this in lab 6. This is your delay circuit. Your delay circuit used 2 flip-flops, but the effect is that the output comes out sometime after the input changes. Well, here we've got 3 flip-flops, so we've got a longer effect, but it's exactly the same principle. So this is pretty simple Verilog code. But let me do one thing here. And I'll put a note here saying don't use a single equal sign. But let's take a look at what happens if we do that. So let's come over here. And let's forget that we were going to use less than equal. And so we'll take this and we'll compile it. And compiles without warnings, without errors. So that's all promising. And let's go ahead and run our simulation. And guess what? Our beautiful shift register is not a shift register anymore. Right? We just broke it. And it looks like, you know, when the input changes, all of our flip-flops, all of our Qs 1, 2, and 3 change at the same time. And here the input goes low, and the next clock tick, all of our Qs go low. We've broken that nice shift register behavior where things move from one spot to another. And the reason it broke is because we got rid of these less than signs. So this equal sign is actually saying, first take your input and do what you have to do to make Q1 equal to that. And only after you've done that, now take the value of Q1 and set Q2 equal to that. And after you've done that, after you've changed Q2, now take the value of Q2 and make Q3 equal to that. And if you wrote these three statements in C, this is exactly what would happen. Each time you executed this, Q3, 2, and 1 would all be equal to N. But when you have these arrows, you're saying at the same time, take your input, copy that to Q1. At that same moment, copy Q1 to Q2. At that same moment, copy Q2 to Q3. So the current value of Q2 at the clock tick, that's what goes into Q3. Not the value of Q2 after it's been set equal to Q1. So this is parallel code. This is happening at the same time, and that's what we always want for this class, at least when we're doing Verilog. So make sure you have those less thans. And when you're building your shift register, if your shift register is doing something more like this, instead of shifting, go back to your Verilog, make sure you got those less than equal signs. Okay, that'll save you 5 hours of work on Lab 7. So, bonus for staying 2 minutes late. All right, we're over time. Sorry about that. Cool. Have a good one. I will catch you next time.